Well, in this lesson, we're going to talk about how to graph sine and cosine curves. We're going to graph one cycle of each type. And we're going to talk about all the different transformations that you can have given an equation, how you can turn that equation into the important properties of the graph to be able to come up with the graph, right? So once we have the properties, we'll be able to graph it. So if we compare this to the last lesson, where we were given the graph and we were coming up with the properties. So you can see up here are the properties that we were looking at, okay? And we were given these graphs, and we looked at the curve, and we came up with, let's say, the vertical translation, the amplitude, phase shift period, and so on and so forth. And when we did that, we looked at things like the zero line, and we found the zero line, and we use that to determine the vertical translation and the amplitude. There are other ways of finding the vertical translation and amplitude, mathematical formulas, but when you're talking about the properties and you're trying to identify the properties and ultimately the relationship between the equation, it's almost better to think about them in terms of the zero line. And we'll see that when we're graphing today. And in the lesson, we did talk about turning those properties into the variables that are part of the equation, and that would allow us to write the equation. And again, we're going to do that on a separate day and talk about actually writing the equation. But that's going to be really helpful in doing the graphing today, because when we're graphing, we're given the equation and we have to turn that into the properties. So we want to tie into our understanding of the relationship between the graph and the properties, and how those properties relate to the variables in the equation, and that will allow us to come up with the graphs. So let's, whoops, wrong lesson. Let's head back to the lesson that we want, which is graphing. So we use this this system called the 5 key questions. It's not really an official rule. Or official name of this system. I don't know who came up with that. It's kind of funny in a way, because I talk about it in terms of these 5 questions, but then they're sort of more like 7.5 questions when you really look at it. So I don't know why it's called the 5 key questions, but that's what we call it. So if you ever see that on a worksheet or something like that, then you know that it's just referring to the system by which we have learned to graph. This system is so great in all the different ways I've seen people graph. This one's definitely my favorite. It's really straightforward. It's really step by step. And if you can just remember these questions, and obviously how to answer them, then what you've done all of the work to get the properties that you need in order to draw the graph. And once you've done the 5 key questions and worked out your X scale, the actual graphing part is really, really easy. Okay. So 5 key questions are: from the equation, we look at what is the zero line, what's the amplitude, and we're going to use those 2 properties, the zero line and the amplitude, to find the max and the min. Points on each sine and cosine occur on the max and the min, so we need to know what those values are. Then we determine where does it start, we determine what is the period, and from that we can determine where it ends. Okay. And like I say, we're not really done yet, because then we have to go and work out a proper X scale. And different teachers do that in a slightly different way. So if you're talking to somebody and they do it in a slightly different way, it's not a big deal. Some people may like one way better than others, and it's really a preference thing. But for the most part, in my experience, they are all actually fairly similar. Okay. And so that's that. So the last thing that we need to sort of connect to, or refer back to before we move on, is that a lot of these properties that we're going to be looking at are in relation to the base graphs that have no transformations. So the zero line compared to the base graph, the amplitude compared to the base graph, that kind of thing. We're thinking about how it has been transformed, and we're going to get that from the equation. And if we can recall, the equation is going to be in this form: y equals a sine k x minus c plus d. And sometimes brackets can look a little different depending on how you've written it and depending on which actual variables you have values for, but that's the form of the equation that we need to have it in order to be able to graph. So we've got A, K, C, and D as our 4 variables. We're going to determine what those values of those variables are and use those to come up with these properties. Okay. The final thing before we move on is we need to remember, and I'll just do sine for now, but there are, for both sine and cosine, there are 5 key points. Okay. And again, this is what we have to know this from the base graph. These are properties of sine from the base function that we just need to know. So sine starts at 0, so 0 horizontally. Okay. But then it starts 0 vertically. So it starts at 0, 0, but what we say is it starts on the 0 line. Okay. And this is the base graph, no transformation, so of course it doesn't have a shift left or right, so it starts at x equals 0 as well. Okay, and then it goes from there, it goes to the max, then it goes back to the 0 line, then it goes to the min, then it ends on the 0 line. And for sine, those are your 5 points, and we have to find basically the x value and the y value of all 5 of those points. And then we're going to graph it. And when you're coming up with your x scale, what's important is the system we're going to use to determine the x scale is going to ensure that all 5 of those points are lattice points. So again, we've talked about this before. They have to be points where the grid lines meet, in other words. Okay, they can't be between grid lines out in the middle of nowhere. They don't necessarily have to be labeled in the x scale. They don't have to fall in a place where the scale is labeled. That's not what it means. It's just where there's a grid line. Okay. And we will see that throughout the examples that we do. So that's our goal, is to figure out, just to find the location of all those points. And you can see that since I have a point at the max and I have a point at the min, I need to know what the max and the min are. And in sine, you've got 3 points on the 0 line, so we need to know where the 0 line is, right? We need to know these properties in order to graph. So let's take a look at our first example. Again, we're graphing one cycle of each of these. This one's sine. There's a few things that you might want to sort of notice before you get going. But I have a habit, I think it's a good habit, that right before I graph, I always go back and look at the original equation and check these things as well. So 2 things that I notice are, we're graphing sine, because believe it or not, on tests, sometimes people will do all the great work, all the 5 key questions, get all the properties done correctly, and then they graph cosine when it was supposed to be sine, right? So in the end, hopefully that's not too big of a deal. You won't lose too many marks if you've shown your work and you've got the properties down, but you don't want to make that mistake, because that's a pretty straightforward thing to do. So you want to make sure that you notice which of the 2 you're graphing. And then the other thing I always make a mental note of, and notice, but I will come back to, is that the a value, which in this case is 2 over 3, is positive. So there's no reflection. That could be that could be a 6th question. Is there reflection or not that we could answer? I just always go back and double check it before I actually graph to see if there's a reflection. A really good habit here, or trick or strategy, is before you start, and for one like this, believe it or not, this one's going to be a simpler kind of question, I would say. But if you haven't done these before, or if you lack that practice and that experience, you might not notice that some of the variables are missing, and you might misinterpret what the numbers in this question are. That's probably more of a grade 9 or 10 mistake, but it does happen. And in that case, you're going to be in a lot of trouble. You're not going to be able to do much of anything, or all your work's really going to be wrong. So my strategy here is to actually write out the values of A, K, C, and D. And if you remember, when we talked about finding equations, that's the ultimate goal of writing the equation when you're given the graph. Is what you're actually doing is finding A, K, C, and D, because again, once you've found those, writing the equation is virtually trivial. But finding the value of those is the hard work. And it's the same thing. I'm going to take the value of these, and I want to make sure I know what they are, and I'm going to turn those back into the properties. So once I have these down, so this can help sort of structure your thinking and focus you and remind you that the equation might look complicated, but it really comes down to the value of these 4 variables. So A is 2 over 3. It's the coefficient out in front. Again, we compare it to that to think about these things. So A is 2 over 3. Again, it's positive. That's something good to make a mental note of. K is 3 over 2. And C and D, well, what are they? Because they don't seem to be here. Well, so that means in this case, C is 0 and D is 0. And that's a little bit different. If there was no A value, you wouldn't say it's 0. You would say it's 1. You're not necessarily getting marked on determining what the A value is. So, if you wrote that down wrong, you may not lose a mark necessarily, but the A value and the K value would be 1 if they weren't there, whereas the C value and D value would be 0. Okay. So I've written those out, and now I make sure that I've got all 4 of those. Again, that's going to be great when we're given the graph and we can write the equation, because it's going to make it a similar process, but it can also help you focus your answer to the 5 key questions that we're going to start right now. So 5 key questions. And every teacher does these in a little bit of a different order for whatever reason. Just the habits that we've got into. The order doesn't really matter. So I always start with the 0 line. And you also don't have to write out all of this. You don't have to number the questions. You don't have to write 0 line. I think it's a good idea to write something, and I'll show you maybe in the next example kind of the way I do it. Or if you look at the solutions, you'll see exactly kind of how I do it. So it can be good to do that. Give something a label, then in case you're looking back at it later, you know why you wrote it. But if you don't want to write all of this, that's fine. Ultimately, your marks... and this again might depend on the teacher a little bit, but ultimately your marks are going to come from your graph. So if you're a bit messy in your work, but your graph is correct, you're probably going to be okay. If anything's wrong in your graph, then immediately what I'm going to look at is I'm going to say, well, their graph is wrong, but did they get any of the properties right? And then if I can't read your work, then you're out of luck. So you do want to show your work as best as you can, as clearly as you can. And so by all means, you can go ahead and write it all out and number them as questions 1, 2, 3, 4, 5. There's nothing wrong with doing that. So the 0 line, as we talked about before, is related to the D value. The D value is your vertical shift up or down, and that's the only thing that impacts the 0 line. So the 0 line is basically exactly the same as the D value. We write it as an equation, so we write it as y equals 0. But that's it. It just is y equals the D value. Okay. 2, second one I like to do is the amplitude. And amplitude, a tricky thing here is, and we talked about this before, if you are asked to state some properties and one of them is amplitude, then you have to do this correct. Amplitude is always positive. So even if amplitude comes from the A value, even if the A value is negative, amplitude, which it isn't in this case, but if it were, the amplitude would still be positive. Okay, so it would be important that you write that. And it is the A value. The amplitude is the same as the A value. And now the reason why I do these two first and I do them together, the order doesn't matter. I could do amplitude first and 0 line. That part doesn't matter. But I do the 2 of them together because the 2 of them make up the max and the min. And I want the 0 line because points land on the 0 line. But I also want the 0 line with the amplitude because I need the max and the min because points land on the max and the min. And this is a little equation. You need to know the sort of formula. You need to just know the relationship. The better you know all of these, as I always say, the faster you're going to whip through this process and save yourself some time. And the way it works is you start at the 0 line, and for the max you add the amplitude, and for the min you subtract the amplitude, and that's all there is to it every single time. So this is 0 plus 2 over 3, which is obviously 2 over 3, 0 minus 2 over 3, which is negative 2 over 3, and this is why I say some of these are trivial, because C and D are not trivial but easier. This is a bit of an easier question because C and D are 0, so it kind of makes some of this work a little bit easier. If you've got fractions, use your calculator if you have to. Make sure you get those fractions correctly. And some people do this backwards, so they flip these two, and that can cause some problems. So don't do that. Start with the 0 line and add the amplitude, then subtract the amplitude. That's going to give you the exact right max and min. Okay. Next question 3 is the start. And the start is equivalent to the phase shift. It's equal to the phase shift, same as the phase shift, which is their C value. So in this case, again, makes it easy. It's just 0. I'll come back to those and we'll talk about them in more detail when we have an example that has a non-zero start. Start's pretty straightforward though. Um, Although that does make me think of this fact that this is something you just need to know. You need to know that the start is the C value. If you don't know that, I'm not sure how you're going to figure that out. So, in your practice, you want to just make sure that you realize that that's where you get the start from. There's no magic to that. It just is the C value. And that is related again to knowing where those variables are in the equation. So the period. So the period has a formula to figure it out. Again, you need to know this formula. It's 2 pi. Remember, it was 360 divided by, but now it's 2 pi divided by k. So this is why we needed to know the k value, which is 2 pi divided by 3 over 2. Now, I'm just going to come off to the side here and do this math. Normally, you wouldn't show all of this. Use your calculator if you have to. Maybe you're good enough at fraction math by now that you can just do this. Obviously, the faster you can do this, the better. Okay, but I'm going to come over here and do this just to show it once. What's happening here is you have 2 pi over 1 divided by 3 over 2, which is 2 pi over 1 times, flip the fraction, 2 over 3. That's how we divide fractions. And 2 pi times 2 is 4 pi. And 1 times 3, pi. And 1 times 3 is 3. So we get a period of 4 pi by 3. Okay? And then the end, well, what's the relationship between the start and the period and the end? And just like we used the zero line and the amplitude to figure out the max and the min, we use the start and the period to figure out the end. We do the exact same thing. So the relationship here is, it is the start, and again, normally I wouldn't write all of this down. We'll just do it in the beginning, the first time, so we've got it written down once to refer back to, plus the period. Again, this is trivial in this case because the start is 0, but you may end up doing some trickier fraction math, and you do not have to show any work for this, so you can just use your calculator. There's a pi in there. Some calculators might be able to handle the pi and spit out an answer that's clear. Some might not. I've shown you before how you can just put the fractions in without the pi button, and but you have to go through the practice and understand how that works. Okay, so there we go. Those are our 5 key questions, but this was kind of an extra question right here. We just included in question number 2, I suppose. And then we're not done yet because we have to figure out our x scale. And this is where everybody does it a little bit different. This is how I do it. I come over to the side here and I call this the critical point distance. Okay, so I just short form it to CP. And the critical point distance, we'll talk about this when we graph it, but this is the distance between those 5 points that we need to graph. You can memorize this process. You don't necessarily have to know that that's what's happening, but that is what's happening, and that is what it is. It's the distance between points, and that's how we're going to break up our scale into a proper scale so that they all fit. So there's a formula for this. It's period divided by 4. Be careful. Sometimes the start and the period can both be sort of fractions, and sometimes people take the start and divide it by 4, and that's just big time wrong. So try not to make that mistake. So we've got 4 pi over 3 divided by 4. That's the period divided by 4. And again, doing the fraction math, this works out to pi over 3. Okay. And let's see. So I do that step, okay, and I show that work like this. Then what I do is I take my phase shift and I just write it down. In this case, it's 0, which is going to make this x scale again a lot easier. When we get into the next example, it's going to better highlight how tricky this can be and exactly how the system works. Okay, and then what I do is between these two, and I like to have them written out just like this so that I can kind of show myself that I'm using this critical point distance that I calculated after dividing the period by 4, and I'm comparing that to the phase shift. And what I have to do is I have to come up with a scale that matches both of them. So imagine this. Imagine your start was 30 degrees and your scale was, or sorry, your critical points had 45 degrees between them. Well, you can't count by 30s. If you count by 30s, your first point will be on there. Great. But 30, 60, 90, 120, right? Your next point's not. If you start at 30 and the distance between your points is 45, your next point will be at 75. The reason why I'm talking about degrees is it's easier to see this in degrees. I'm starting at 30. There's 45 degrees between my critical points. So my next point will be at 75 degrees. If I'm counting by 30s, I'm going 30, 60, 90. I'm skipping over 75, and it will not be a lattice point. Okay? So I have to come up with something that will work for both 30 and 45. And it's quite easy when you're doing it in degrees. I would count by 15s, right? Because 30 will be on there. And when I count by 15s, I'll go from 30, I'll go to 45, then to 60, then to 75. So I'll hit 75. And so when it's, you just look for the lowest, or some, sorry, not the lowest necessarily, but some common factor of those two numbers. And as long as you do that, then you're going to be fine. The problem is when we're talking about fractions, it's harder to see what the common factor is. It's harder to see what the lowest common factor is. So what you're going to do is you're actually going to get the lowest common multiple of the denominators of the fractions. So because this one is just sort of over 1, you could think of it that way. Okay. The lowest common multiple is 3, so it's going to be pi over 3. And then I decide how many squares I want that to be. So I don't want it to be pi over, I don't want my x scale to be pi over 3, because then there would be, the distance between my points is pi over 3. So it would be like every point would be 1 square. I don't know if you can see that yet, but hopefully after we've graphed a couple of times, that'll start to make more sense. It'd be worth coming back and maybe even listening to this again and thinking about it. Okay. But this is going to be, this number that I'm about to pick is going to be the scale that I'm counting in my x scale. So how many, every time I go over, what is it, right? What's the distance between the grid lines? If it was pi by 3, then my points would just go there, 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 there. Well, that's too small. Okay, you're not allowed to leave it, you're not allowed to have it be that small. So I'm going to say, therefore, I'm just going to make this 3 squares. Okay, so I'm going to say pi by 3 is 3 squares, which means, now, and you don't necessarily have to know this part, but it means 1 square is pi by 9. Okay, and that's because 3 times 3 is 9. So if 1 square is pi by 9, when I count 3 squares, that will be pi by 3. You could do 4 squares instead. That would give you pi by 12. And 4 squares between points would be fine. I'd have lots of room on this grid for 4 squares between points. If I did 12 squares between points, my graph would probably go off of this grid. If I only did 1 square between points, you're going to lose marks because it's just too crushed down. Okay, it's got to be more spread out than that. So you just have to make it look reasonable. So 3 squares, 4 squares, 5 squares, 6 squares, something like that is usually reasonable. Okay, as long as all 5 points fit on the graph. So I've decided that pi by 3 will be 3 squares, and that's how I'm going to do my x scale. So this was all determining our x scale. Okay, so it can be a little bit tricky. It can be even a little bit trickier when you've got a phase shift that's not 0. The next example will show that. And I think a lot of people get confused about this whole idea about the relationship between pi by 3 being 3 squares. That means how far, what's the distance of 1 square, but you don't actually necessarily have to calculate the distance of one square. So you might be able to get away with just skipping that step, not thinking about it. But I like to think about it. Sometimes I find it helpful. And that's it. Now we've done the hard work. Now we just have to go back and remember where the 5 points are for sine, where they are in relation to the properties. I've got the properties, so we're good to go. The first point occurs on the 0 line and at the beginning, which is your start. So my start is 0, my 0 line is 0. So in this case, my first point is 0, 0. I can pretty much guarantee that it won't be that easy on the test. Okay, we're starting with the simple one. Now I know, this is where I go back and I check, okay, make sure that I'm doing the right one. I am doing sine, that's correct. And it's not flipped. There's no reflection. So as long as there's no reflection, after the first point, sine goes to the maximum. Okay, and you need to know that. That's just something you need to know. You need to know the pattern of the points, where they go, each of the 5 points, where you start and where you go from there. Okay. And oops, I haven't actually labeled anything. I got ahead of myself because that first one was so easy. So I got to label the x-axis. Sorry about that. So pi, remember I said 3 squares was pi by 3. That means 1 square is pi by 9. I'm just going to talk about this because I think it does help us sort of make some connections between the fraction math that's going on here. 1 pi by 9, 2 pi by 9, 3 pi by 9, which is pi by 3, right? So that all does make sense. So 1 pi by 3, 3 squares to 2 pi by 3, 3 more squares to 3 pi by 3, but that's actually pi. So this is how I expect you to label your scale. You could be labeling every 3 or every 4 depending on how you've chosen your scale and how you've laid things out. Okay, you definitely don't want to be labeling every single square. Okay, so every 3 or every 4, every 5, not usually every 5 in trig, but something like that, 3 or 4 usually. But with reduced fractions, so when don't label it as 3 pi by 3, label it as pi. 1, 2, 3, 4 pi by 3, but notice how I'm counting in pi by 3s. 1, 2, 3, 5 pi by 3. 1, 2, 3, 6 pi by 3, but hopefully you've caught on and you realize that's actually 2 pi, so I'm going to label it as 2 pi. Now my rule, again, for my test, my expectation is that your scale labeling goes past the furthest point that you're going to be graphing. Well, this graph is going to end at 4 pi by 3, so I've definitely gone far enough. I went a little bit further just to go to 2 pi, so it wasn't that far. It was a good practice, but it has to go at least as far as the last point. I'm going to go back a little bit just because, this would be negative pi by 3. Usually there are going to be points back there, so you would have to label back there. This time there isn't. This question's a little bit trickier because it's got a fractional a value. So my vertical scale has to count by thirds because it's 2 over 3. I could make 1/3 2 squares. I think that would fit in this case. 1/3, 2/3, 3/3, which is 1, so I could do that. I'm not going to because I wonder if that's going to be a bit confusing for people. That would stretch this graph out a little bit more nicely, but I'm just going to go 1/3, 2/3, 3/3, which is 1, and I'm actually just going to label it at 1, and then 1, 2, 3 more to 2, 1, 2, 3 to negative 1, 1, 2, 3 to negative 2, and again, you don't have to label the entire graph. You have to label at least as far as the points go. So this is going to be more than enough for this graph. Now we're ready to graph. I'm going to go back and put that on there. Now I know a couple of things. Remember we talked about this? Sine now goes to the maximum. I need to know 2 things. So the maximum is 2 over 3. Okay, so let's keep that in mind. Let's not forget that. But this is where this comes in. I made the distance between critical points 3 squares. This is the decision that I made. That made 1 square pi by 9, but even if you didn't think about that, I know that I just chose pi by 3 to be 3 squares. So I'm going here and I'm counting over 3 squares. 1, 2, 3, and I'm going up to the maximum, which is 2/3. And since I'm counting by thirds, I just go up to 2 of them. 1, 2, 3 more, and sine is back on the 0 line. 1, 2, 3 more, and now sine is at the minimum. 1, 2, 3 more, and sine is back on the 0 line where it ends. And take a look at that. I ended in the ending that I calculated. So there's my check that I've done everything correct, a really good check to do at the end. Notice we haven't used the end up till this point. So you might even say, why is that one of the 5 key questions? Well, I keep it in there. Some people do these things a little bit differently and they use the end in a bit of a different way. But the way I do it is I just use it as my check at the end that I landed in the right spot. Okay. And I have to make sure that there's the same number of squares between each of my points. Students do that wrong all the time, and they count 3 squares, then they count 4 squares for some reason. So if 3 squares is what you've calculated, it might seem a little bit strange to be counting squares and that kind of thing, but trust me, it makes the process easy. So I knew it was going to be 3 squares, so I make sure there's 3 squares between all of my points, and I make sure I end at my end, and that I've got my maximum in and everything right, and I've got sine drawn correctly. Okay, so now I'm going to connect these points. Sometimes it takes me a couple of cracks to do it on the computer because it's a bit tricky, but that one went pretty good. That looks pretty good. You are not allowed to make your sine graphs look like this. Okay, no sharp turns, no straight lines. It does have to be a curve. I always say no hairy lines. If you don't know what a hairy line is, a hairy line is this. Let's say I was where you kind of shade it in along the way. I know it's a little bit tricky at first, but do some practice and maybe do it a little bit at a time like me, where you do that first and then you try again afterwards for the next part, and practice until you can kind of get a nice smooth curve all the way through. Okay, it should look at least somewhat like a sine curve when you're finished. Again, this graph turned out to be really easy because all 5 of my points did land where the grid is actually labeled. So that all just kind of fit and all felt nice. But that is definitely not always going to happen. Our next example is going to highlight that nicely. That definitely doesn't always happen. Okay. All right. So there's a sine curve done using the 5 key questions method. Let's move on to the next one. Let's get right into it. This one's going to be a little bit trickier because it's got all the different values and it's got some other quirks to it, a couple of things that are going to be more challenging. But it's got one other thing to it, and this isn't going to come up very often in our course. I think it does come up a little bit in grade 11, so we're going to remind ourselves of it. But, it won't come up for us too much. But it is an important thing to realize about all kinds of functions. I'll whip right back up here for a second. If we look at this, okay, you'll notice the next example is cosine. We didn't talk about that yet, but it's cosine. But if I wanted this to be cosine, I would just erase that and write cos, right? That part of all of this is exactly the same. Whether you write cos or sine, it's all the same. The A, the K, the C, and the D all look the same. So what I'm looking at here is this part, and I notice that it's K times the bracket of X minus C. Well, nothing in math is sort of willy-nilly where you can either do it that way or not. So if that's how the relationship is, that's how it has to be. Math is very picky that way. And notice we don't have that in this case. So what does that mean? That means this is not in proper transformational form, and we have to put it in transformational form before we can do this work. So how are we going to do that? We have to factor the 3 out. So it's in brackets like this. Now, I'm not going to talk about we've talked lots about fraction math, and it would take all day for us to go over this every single time we come across it. But you can kind of take my word for it. If I do 3 pi divided by 4 and divide it by 3, I get pi by 4. Some of you are probably going to be able to see that easily. Some of you maybe not. Again, you can use your calculator, or you can think about how the math actually works. You're multiplying by a third, so the 3's cancel, right? However you want to look at it, but that's the way that works out. You could also quickly compare it to if you have 2x plus 4 Well, when you pull out that 2, it's 4 divided by 2. That's how you get it, right? So that's why I did. And that's obvious when you're looking at numbers like that. Not as obvious when you've got a fraction involved, I know. But that's what you would be doing is 3 pi by 4 divided by 3, okay? So now it's in transformational form. Now I can write out the A, the K, the C, and the D. That's our strategy to keep things as simple as possible. And as I'm doing that, look at what I'm observing. I'm observing that the A is negative, so this has a flip. So I can make a mental note of it now. You can write it out. You could write it right above the grid. You could, like, whatever works for you to make sure you don't miss it when you actually go to graph it. Okay, and that's another nice thing about this strategy is when you write it out, you hopefully will make that mental note. K is 3. C is negative pi by 4. It has the opposite sign of what's in the brackets there. Okay, and D is 1. Now, the C, notice it would have been wrong. If I had chosen this as C, and I've had students ask this, well, what if I just did it that way? What if I did it a different way and I did it with that as the C? And I say, well, then your graph would be wrong. Like, the thing that you would draw would not be this function. If I put this function into a computer to graph, it would look a certain way, and it would look like this. So your graph would be wrong. Now, that would be 1 mark on a test, probably something like that. It might make it a way harder graph to draw. And again, this won't come up very often in this course, so it's not something to worry too much about. But it is a thing, okay? So there we go. Now we've got our A, K, C, and D values, and we can start our 5 key questions. So question 1, I might just do ZL for 0 line. Instead of writing the whole thing out, I might not even put question 1. You might just write, 0 line like that. Okay. And remember, it comes from the D value. So it's Y. Whoops. So it's Y equals 1. Next, amplitude. So amplitude is always positive, so that's just positive 2. Max and min is the 0 line plus the amplitude and the 0 line minus the amplitude. Again, you've got to get that in the right order. So 1 plus 2 is 3. 1 minus 2 is negative 3. I've seen students do this backwards consistently, and I tell them not so much in grade 11, really, or grade 12. It's more a grade 11 mistake, but and you say over and over again, don't do that, and they keep doing it, and so they've got everything backward. This is wrong. Negative 1. They've got their signs all mixed up, right? So the max and the mins are wrong. So be very careful of that. Okay. 3, start. So the start is equal to the C value, so it's negative pi by 4. Okay, the C value has the opposite sign of what's in the brackets. The direction of your shift is the opposite of the sign in the brackets, but those two things are the same. Okay, 4 is the period. Again, it's 2 pi divided by the K value. Well, in this case, we're done. 2 pi by 3 is just 2 pi by 3, right? So we don't have to do any work there. And the end is the start, including the sign, plus the period. Now, however you, again, notice that this is a lot harder because all of a sudden you've got fractions that you have to work with. If you're starting to get good at fractions because of all the work we've done with radians, fantastic, and you may be able to do this easily. The way you would do it is with the common denominator, which is going to be 12. So this is going to be negative 3 pi by 12 plus 8 pi by 12. Negative 3 plus 8, which is positive 5. So this is going to work out to 5 pi by 12. But again, you don't have to show that work, so you can just use your calculator if that's what you have to do. One way or another, you need to do that accurately, and you do want to do it quickly. So even if you're challenging yourself trying to do it in your head, as long as you're getting it right every time, that's great. If you're making mistakes, then it's time to pick a new strategy. But it's also, if it's taking you a long time when you're writing a test, maybe you don't want to go through that challenge and you just want to use your calculator. Finally, we're going to do our X scale. So we first find our critical point distance, okay, which is the period, divided by 4. So this works out to 2 pi over 12, which is pi over 6. Okay, and then my phase shift, whoops, which is negative pi by 4. I don't actually need the negative here. I'm going to write it for consistency because it might be confusing if I didn't have it. But we're not really worried about whether it's positive or negative at this point. But we're worried about the 6 and the 4. Now, this is an interesting example because it's what I talked about before. Pi by 6 is 30 degrees. Pi by 4 is 45. So I have to figure out something that I'm counting by as I'm counting squares that will get both of those, right? And so what I do is I just get the lowest common multiple of 6 and 4, which is 12. And so it's going to be pi by 12. Okay? But then I have to decide how many squares that's going to be. Okay? And here's how it works. Don't write this down yet, just watch. The relationship is between the critical point distance and that number that we just came up with. And in this case, it's 6 times 2 to get to 12. So that would be 2 squares between points. That's not enough. I'm going to go further. So I'm going to say pi by 12 is equal to 2 squares. Whoops. Which means I multiply by 2 again, and therefore there are 4 squares between points. That means 1 point is, because I multiplied this by 2, 1 point is pi by 24. But again, I don't really need to worry about the number pi by 24. That's not going to factor in. That's not going to matter. Okay. So what I need to know is this is really important, that there are 4 squares between points. And I need to make sure that I'm using the critical point distance for that, not the phase shift. The phase shift helped me come up with the 12, but not the distance between points. Okay. I know that's convoluted. There's not necessarily an easier way. There are different ways of doing it, and you know, students and teachers might argue about what the easiest way is, but ultimately what I'm going to tell you is it's not that one way is easier or other. So people have their preference, that's fine. But any of the methods require some practice. None of them are super easy. A big part of that is just because it's fractions and we're not used to it. And you just have to practice and go through it enough to have done it a bunch of times so you've got it. This seems convoluted, but it is a step-by-step process, right? The relationships are just strictly right there. So once you've done it enough times, you just remember that that's how you do it. You remember that you take your period and divide by 4. You come up with a common multiple of that number, your critical point distance and your phase shift, and then you decide how many squares that is. Okay, so now I'm going to take that and I am going to start my scale. So remember, 2 squares is pi by 12. So there's 1 pi by 12. There's 2 pi by 12, but 2 pi by 12 is pi by 6. So this is how I'm going to continue my scale. And I'm going to just label every other, but I'm going to sort of mark every 2 just because that's going to make it easy for me to make sure I'm not missing any. So 1 pi by 12, 2 pi by 12, 3 pi by 12, 4 pi by 12. But 4 pi by 12 is also 2 pi by 6. But 2 pi by 6 is also pi by 3. And again, this is where it does get more challenging, where you have to be doing this work to make sure that you've got your scale written out correctly. Okay. So now that's 2 pi by 6, 3 pi by 6. 3 pi by 6 is pi by 2. 4 pi by 6. 4 pi by 6 is 2 pi by 3. 5 pi by 6, which is just 5 pi by 6. 6 pi by 6, which is pi. Now, I've gone way past the point that I have to. But I think there's some neat relationships here, so that's one of the reasons why I did it. You don't have to do that. You may not know exactly where your last point falls, so you may not. You may just kind of keep going until hopefully you've gone far enough, and then if it's not far enough, you go further. But take a look at this. This was 1 pi by 12, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12 pi by 12, which is pi, right? Like you can think of it that way. Or 1 pi by 6, 2 pi by 6, 3 pi by 6, 4, 5, 6 pi by 6. Or 1 pi by 3, 2 pi by 3, 3 pi by 3. Like this is really good understanding of fractions right here, right? And all these relationships. And I think going through this process and trying to do some of it in your head helps you understand it better, and you'll get faster at it. Now remember, we do have to go back into the negatives here as well a little bit. 2 pi by 12, 4 pi by 12 negative, which is negative pi by 3, and that's far enough, so I'll stop there. Okay, and our other scale, our max and min are 3 and negative 1, so I'm going to count by 0.5, so I'm going to say this is 1, 2, 3, 4, to stretch things out, and negative 1, negative 2, negative 3, negative 4, and again notice that I did just kind of do the whole scale because it only takes a second to make sure that I get past my max and my min. Okay, so labeling the scale is tricky. Determining your scale can be tricky, but once all that's done, hopefully the rest is fairly easy. This is a challenging one. This one's harder than a lot because of the relationship between the critical point distance and the phase shift. Okay, so now I have to figure out where I start. I don't start on the zero line. That's sine. This is cosine. I'm remembering that I have reflection. So cosine usually starts on the max. Again, that's something you just need to know, but it's reflected, so it's going to start on the min. So we're going to start at negative 1. Okay, and we're going to start at negative pi by 4. Well, where's negative pi by 4? Well, it's not on here. So how are we going to figure it out? Well, I'm not sure that there's necessarily an easy way to do it, but if we've done all our work correctly, it does have to be on here. Remember, these lines are pi by 12s. How many pi by 12s is pi by 4? 3 pi by 12 is pi by 4, right? Think about that. 3 pi by 12 is pi by 4. So 1 pi by 12, 2 pi by 12, 3 pi by 12 is pi by 4, and I start at the minimum, so there's my first point. Now I'm going to think about this in another way as well. We're not allowed to do any of the work in degrees, but that doesn't mean you can't think in degrees sometimes in your head. Pi by 6 is 30. Pi by 3 is 60. What's right in the middle? 45. Okay. So I chose 4 squares between points. So 1, 2, 3, 4. And I go to the 0 line, which was 1. 1, 2, 3, 4. And I go to the max, which was 3. This is just all the information that we've already determined. 1, 2, 3, 4. Back to the 0 line. And 1, 2, 3, 4. Back to the minimum, and there are my points. And what is this? Well, it's 1, 2, 3, 4, 5 pi by 12, which was our end. So it looks like everything matched. Try to get a nice smooth curve, make it as symmetrical as you can. Mine wasn't great. Like I always say, it's a lot harder on a computer. That is that one. So you can see how it's a lot trickier because of all of the work with the scale and even labeling the scale. It's a lot trickier, and it just takes some practice. It's definitely doable. It's not impossible. Don't think that it's impossible. Don't think it's too hard. It just takes practice, and it takes some getting used to, and after running through this a few times, you will get there. Okay. There is one more example here. We're not going to do it. We don't have time. Okay, I'll leave it as an extra example for you to do. If I get a chance, maybe I'll make a video of it and I'll throw it up online. Otherwise, the solution to it will be online as part of the scanned lesson, so you can check the answer yourself if you like. There's nothing all that different about this one. It's just more practice of the same. Again, it does have some thinking to do in terms of the X scale, but it's not and complicate it even more or any more way. Okay, so it's just another good one to practice. But there's two, a simpler one and a trickier one. And remember, you just have to remember the steps. The 5 key questions does turn this into a step-by-step process, and you just have to go through those steps, and you just have to practice how you come up with that X scale, and how many squares there are between points, and how you're going to label your scale. And once you've got that, you'll find that this process actually is fairly straightforward, and just fairly step by step. You can turn it into that process, but it can seem overwhelming at first. So good luck with the practice. And if you're getting frustrated with the scale, by all means, ask those questions, and we'll talk about it. And every time you do it, it will get a little bit easier and a little bit easier and a little bit easier. And eventually you'll realize that it's starting to come together.